class, I now want to talk to you about renal failure. This is covered in chapter 33. Really, what I want to focus on is how we calculate or determine if a patient is in renal failure. This all comes down to renal clearance values. Most schools do not teach renal clearance values in physiology. We do at Saddleback. So if you would like to join us for the lab, we will be doing renal clearance values probably in the next week to 2 weeks. So when you hear this lecture, and if you're interested, you should email me right away. I'd be more than happy to have you come into the lab and do some renal clearance problems. It's very clinically relevant. I'm going to give you just a little synopsis of that to explain renal failure. There are some important terms to know, like renal blood flow, effective renal blood flow, renal plasma flow, effective renal plasma flow, GFR, which stands for glomerular filtration rate, filtration fraction, as well as filtered load, excretion, and renal clearance values. I'm going to talk about what these terms mean, and I'm also going to tell you how we calculate GFR, which is an indication of renal health. Before I begin, I want to set the stage. Ask yourself, what are we interested in? What solute in the blood are we talking about? Can it be filtered across the filtration membrane? Is it reabsorbed by the nephron? Is it secreted by the nephron? Each solute in the blood, each waste product, anything in the blood is going to have different properties. Some solutes are freely filtered and 100% reabsorbed. An example of that would be glucose. Some solutes are freely filtered and could have variable reabsorption and variable secretion. Potassium is an excellent example of that one. It all depends on the body's needs, right? So we have to stop and ask ourselves these questions for any solute. What determines if something is filtered, reabsorbed, or secreted? Well, the size of the solute, its permeability, the surface area for filtration, a lot of that will determine if it even can be filtered in the first place. What about reabsorption and secretion? A lot of solutes have varied reabsorption and secretion, like your electrolytes. It will depend on their normal values, and if your body has deviated in some way, like your acid-base balance, which we're covering this week. So we need to stop and ask these questions anytime we are talking about something that the kidney might be processing. Are we talking about glucose, or creatinine, or potassium? Then we need to also invite layers of questioning like, is the patient in acidosis or alkalosis? There are lots of questions to ask and consider. Okay, so let's start from the beginning. Let's talk about important rates and values. Now, your cardiac output is 5 liters per minute. That is how much blood your heart is pumping. On average, the calculated average is that 1/4 of this blood actually goes to the kidneys. That means about 1.25 liters per minute of blood is actually going in and out of the kidneys. We call that renal blood flow, or RBF. The actual value is probably closer to 1.2 liters per minute, and I will explain why. Stop and think. Of that 1.2 liters per minute, how much of that is plasma? Plasma is the only part of whole blood that is actually filterable, right? That is the part that can cross the filtration membrane. So 55% of whole blood is filterable, is the plasma. The other part is the red blood cells. That's your hematocrit, which is usually about 45%. So of this 1.2 liters per minute, 55% of that roughly is plasma. If I multiply 0.55 times 1.2, I'm going to get 660 milliliters per minute of plasma arriving in the kidneys. Now this is including both kidneys. That value is called renal plasma flow, or RPF. Do you think that all of the plasma arriving in the kidneys, 100% of the plasma, all 660 milliliters per minute, is instantly being filtered? No, it can't happen. Otherwise, how would the red blood cells that don't get filtered tumble out of the glomerulus into the efferent arteriole. Only about 20% of the renal plasma flow is actually filtered. The amount of plasma that actually enters Bowman's capsule is about 125 milliliters per minute. That volume is called GFR. It is your glomerular filtration rate. Your filtration fraction is how much filtrate actually gets into Bowman's capsule compared to how much plasma flowed through the kidney. By the way, we can't call it plasma once it's filtered. We have to call it filtrate. So your filtration fraction is 125 milliliters per minute divided by 660 milliliters per minute, which is approximately 20%. That's your filtration fraction. How much urine is being produced? 2 milliliters per minute is how much urine is being produced. That means you can have about 120 milliliters produced in an hour. Obviously, I'm entertaining a well-hydrated person. It would be considerably less if someone was very dehydrated. The amount of urine that is formed is only about 1% of the total plasma that arrived in the kidneys. Let's do this all again, slide by slide. Renal blood flow is the amount of whole blood that actually goes in and out of the kidneys per minute. We are talking about volume per minute. Renal blood flow is loosely calculated as 1/4 of cardiac output, which is about 1,250 milliliters per minute. That is assuming that blood vessels are fully dilated. It turns out that from moment to moment there is some slight vasoconstriction in your renal arteries and vessels within the kidney. In actuality, when we adjust for this, renal blood flow is about 1,200 milliliters per minute of whole blood that is flowing into the renal arteries and out through the renal veins. That is a lot of blood flow. What is effective renal blood flow, or ERBF? When we are talking about effective renal blood flow, ERBF, we are recognizing that there are two types of cells in the kidney. There are the cells in the kidney that constitute the nephron that are actually processing your filtrate. These are called parenchymal cells. But there are also support cells, stromal cells. How much of the whole blood that is arriving in the kidney is actually going to be filtered? How much is serving the needs of the support cells? We need to differentiate this. Only about 90% of your renal blood flow is actually going to go through the glomeruli. If I were to take 1,200 milliliters per minute, RBF, and multiply that by 0.9, I would get 1,080 milliliters per minute. That is the amount of whole blood that can actually go to the glomerulus and be processed by the nephron. Of course, we recognize that it's not whole blood that is filtered. Only the plasma portion is filtered. We really should be more interested in renal plasma flow, which is the amount of plasma that actually goes through the renal artery and out the renal vein per minute. How can I calculate renal plasma flow from renal blood flow? I would need to know the patient's hematocrit. If I know the hematocrit, I can take that value and subtract it from 1. If I subtract the amount of red blood cells in the whole blood, I will be left with a fraction that is plasma. If I take an average hematocrit of 0.45 and I subtract that from 1, 1 representing whole blood, like 100% of blood, I would get 0.55. If I then multiply 0.55 times 1,200 milliliters per minute, which is renal blood flow, I will get a renal plasma flow of 660 milliliters per minute. We recognize that not all of that 660 milliliters per minute of plasma will actually get to the glomerulus and be filtered. Some of that plasma is going to serve the need of the stromal cells. Only 90% of the renal plasma volume actually goes to the glomerulus. If I were to multiply 660 milliliters per minute times 0.9, I would get 594 milliliters per minute. That is known as our effective renal plasma flow, ERPF. Again, what does that mean? That is the volume of plasma that is actually going through the afferent arteriole leading to the glomerulus, which could be filtered. What is glomerular filtration rate? Well, of that 594 milliliters per minute, do you think all of it actually goes through the filtration membrane, through the glomerular capillary, and into Bowman's capsule, or the glomerular capsule as it's supposed to be called now? If you look on slide 8, down at the bottom left corner, that little structure that looks like a red carnation is my way of drawing the glomerulus. All of the 594 milliliters per minute of plasma that is flowing through the glomerulus does not get into Bowman's capsule. Only about 20% is filtered. That is a high filtration fraction. I determined that by dividing the GFR by the RPF. Again, it is about 20%. Glomerular filtration rate, GFR, is roughly 125 milliliters per minute. That means your plasma is filtered many, many times a day. You actually filter 180 liters of plasma per day. That is an enormous rate. We are going to use a standard GFR of 125 milliliters per minute. That is considered a healthy value for renal function. What is filtered load, aka tubular load? Filtered load is the amount of any non-protein or non-protein bound substance that can move from the glomerulus into Bowman's capsule. Now stop and think. Do we have sodium dissolved in our plasma? Yes. Do we have glucose dissolved in our plasma? Of course. Are they dissolved in equal quantities? Do we have equal amounts of sodium and glucose or potassium? Absolutely not. So I want you to think of this. I want you to think that you are going to take a glass of water, and I want you to sprinkle some salt in that water. Then I want you to take a teaspoon of sugar and a cup of Crystal Light and add all of this to the glass of water with the salt. Dissolve them in this glass of water. Don't drink it. Now pour half of that glass into another glass. Let that amount of volume that you poured into the second glass represent GFR. That is volume per minute. It represents the amount of plasma per minute that exits through the filtration membrane and enters Bowman's capsule. Let filtered load represent the amount of substance dissolved in that volume that enters Bowman's capsule. When you poured out half of your glass into a second glass, did you pour equal amounts of salt, equal amounts of glucose, and equal amounts of Crystal Light? Did they get into the second glass in equal amounts? Absolutely not. Why? They didn't get into the second glass in equal amounts because different amounts of each of the solutes were dissolved in the first place. Filtered load is basically calculated as GFR times the concentration of that substance in the plasma. In other words, how much volume did you pour into the second glass times the concentration of the solute in that fluid that we just poured into the second glass. That is filtered load. It is GFR times plasma concentration of a solute. If you compare what was actually filtered, that means what actually entered Bowman's capsule, versus what was actually excreted in the urine, it will tell you if that substance is reabsorbed or secreted. What do I mean by that? If we look at slide 10, we have 4 different substances. Let's start with substance A. Substance A is freely filtered. You see some plasma arriving in the glomerulus along with some of substance A dissolved in the plasma. We recognize that some plasma gets into Bowman's capsule, about 125 milliliters per minute, and so would some of substance A. Substance A is not reabsorbed nor secreted, so whatever is filtered will end up in the urine. The best example of that is inulin. a substance I'm going to tell you about in just a little bit. What about substance B? Look at this picture. Substance B is filtered and partially reabsorbed. Would we expect the same amount showing up in the urine as what was filtered? No. We would expect less showing up in the urine. That is what I mean by E, excretion, being less than FS, filtered load. Excretion will be less than the filtered load. An example of that would be sodium, which has variable reabsorption. Again, your needs of sodium depend on your diet and your excretion. What about substance C? Substance C is freely filtered but completely reabsorbed, meaning that you should not detect any of it in the urine. In this case, the best example is glucose. There is 100% complete reabsorption of glucose in a normal, healthy individual. Substance D is a substance that is freely filtered, but it is also secreted, which means that you would expect to have more of that substance detected in the urine than what was filtered. Again, in this case, I would say that E is now greater than filtered load. What is excreted is greater than the tubular load. The best example of that is a substance called para-aminohippuric acid, or PAH, which I am not going to talk about in this lecture. We are now trying to calculate excretion. In the previous slide, we covered 4 different substances with varying degrees of excretion. Either what was filtered was either secreted, or what was filtered was partially excreted and was reabsorbed or partially reabsorbed, or what was filtered was 100% reabsorbed and not excreted. Or in the case of substance D, what was filtered was also added to through secretion. What we detect in the urine, excretion, was much larger in this case than what we calculated for filtered load. There are several ways that we can clinically evaluate or calculate the excretion rate of a substance. Each substance needs to be calculated independently. Now I don't want you to memorize these equations at all, but look down at the bottom one. The simplest way that a clinical lab tech can calculate excretion is by multiplying the amount of urine production, the amount of urine in milliliters per minute or liters per hour, times the urine concentration of whatever substance they're monitoring. How do they measure the amount of salt in a patient's urine sample? Well, they take the urine sample, they put it in a spectrophotometer, and they can actually analyze the concentration of salt and sodium, sodium in that urine. It is easy to do. They can calculate the excretion rate for any particular substance. They simply collect the urine and then pop the urine sample into a spectrophotometer and measure whatever substance they want.